Hello everybody and welcome to this webinar about handling flexible bodies in multi-body simulation. This webinar is brought to you by EngineSoft. EngineSoft, which is a private group that is very active in CAE world with branch offices in both United States and Europe. Today I'm talking of this topic with specific focus on RecurDyn software's features, because RecurDyn is the software that I've chosen after many years of activity in this field for his capabilities and its incredible amount of features to properly set up flexible multi-body models. So the agenda of today's meeting is very short in the number of points, but very dense in terms of topics. First of all, I will discuss a little bit when it's proper to use flexible bodies, because this is not mandatory, but in case we need it, we have to know how to do that. How to get the flexible bodies in RecurDyn. And then I will discuss the two approaches that are available in RecurDyn to make flexible bodies. One is called full flex, and the second is called reduced flex, and it's basically the model reduction method formulation that is available in a number of other softwares. And finally, I will talk about an example that comes from my professional experience, where you can see how important it is to make the right choices in defining the model. As said, rigid multi-body simulation is the starting point in multi-body. And this approach is by no means useless or trivial. We still use rigid multi-body very frequently, and it's the best possible approach in terms of efficiency, calculation time. So whenever you have to perform just kinematic analysis or interference check, whenever your dynamics is slow and you don't expect to have large deformations of your bodies, whenever you just need to check for functionality and your model only features lumped properties, stiffness, damping, that are located in very precise points of your model, you can rely on rigid multi-body. This is always the starting point to not waste time. Of course, once you have a well-done rigid body model, you can make a step forward and convert a number of the included bodies into a flexible body. When do we need flexible bodies? I think there is not a precise answer to this question, but I tried to find certain situations where this is at least recommended. For sure, if we have deformation of bodies and this deformation is changing the application points for forces and constraints, then in that case we have to have flexible bodies. The second situation that comes from my experience is when you have vibrations in the system due to natural frequencies of the flexible bodies, of course, and these vibrations are happening at the same frequencies of the motion that you are trying to investigate. The third situation where you might be forced to use flexible bodies is when you are performing multi-body simulation, but you also want to have some structural outputs from your model. Then you have to go for flexible bodies, of course. Finally, it's not maybe the most important, but if you have systems where your body are connected to other bodies through a large number of constraints, then you are in a hyperstatic, I would say hyperdynamic conditions, because it's not static, but it's an over-constrained system. To be solved requires the stiffness of the system. So in that case, you must use flexible bodies to get the internal reactions. When I say largely deformable systems, I'm talking of this kind of application. So on top, you see there is a coil, and you can imagine this is paper or even a thin film. It can be whatever you like. If you want to perform this simulation, of course, you cannot avoid the use of a flexible body. In this model, there are many contacts applied to the flexible body, and the large deformation is, of course, mandatory. The same applies to the simulation below. That's a spring, and it's commonly used in watches, mechanical watches. So the size of this spring is very small, but it's the source of energy for your mechanical watch. In this case, we have simulated it using flexible beams, and as you can see, again, there are plenty of contacts on the flexible body and very large deformations in this winding operation. Both situations require flexible body, but even in apparently simpler situations, you need flexible body. Look at the example on the right. Here I'm considering two beams. Both of them are fixed at the bottom. On the right beam, I have a rigid body, and I placed in the constraint a spring, so lambda approach. And this rotational spring has the stiffness that you might calculate analytically for a beam. It's a cantilever beam, so all the formulas are well known. On the left, I made the same beam, but it's flexible, and I used one of the formulations available in RecurDyn. So the two beams should behave in the same way, because one is fixed, the other is fixed through a spring, but the spring has the stiffness that is calculated properly. And I'm pushing the two beams with the same force. What happens? This is the result. The same force is giving completely different results on right and left. And the reason is very simple. Since we are having large deformations, the linear theory that is used to calculate the stiffness placed at the constraint on bottom is no longer valid, or at least it is approximated. The real deformation, the real position of the beam after the application of the load, is on the left, obtained only using flexible bodies. In this slide, you can see what I mean for coupling between natural frequencies and system dynamics. The injector on top is operating at very high speed, because when the electric actuator opens the pin, it moves at speed of light. And in this case, all the vibration modes of the spring are excited, and you cannot predict the reactions and the behavior of the pin if you don't include the full flex spring. Additionally, I can tell you, if this is a controlled system, as they are actually, you cannot set up the control system properly if you don't include in the model the spring with its distributed mass and distributed stiffness. In the video below, you see a tower crane. This system is not really an example of high-speed dynamics, so apparently you could say there is no need of a flexible multibody, but you would be wrong. The reason is that this system has very low natural frequencies. We are talking of fraction of hertz. So even if the motion of the car of the tower, of everything is slow, and you have very, let's say, smooth and mild operations on this system, since the natural frequencies are quite small as well, you need to take into account flexibility. And one example is very simple, I think you can understand better. When you activate the motor, which is at the end of the tower and at the connection between the tower and the arm, you start applying the load, the torque to move the arm. Then the end of the arm, which might be 50 meters away, is still standing even when the tower starts moving because of the flexibility. So the control system that is asked to govern the torque amount to move the arm without unexpected oscillations cannot be tuned if you don't include in the model the flexibility of the tower and the arm. The fourth example is a valve train. We will see it later in a better way. In this case, we have again a fast dynamics like the injector, and you need to include a full flex model for the spring if you want to predict correctly the valve lift. This is probably the easiest to understand. In these two models, we wanted to get the prediction of the stress that is caused by dynamic response of the system. And so we had to use flexible bodies. It's important to remark that the dynamics can amplify up to 10 times or even more the internal loads and the stresses that you can get on flexible bodies. So performing flexible multi-body simulation is not just a check. It's important to get the loads to use later for finite element refined analysis. And finally, it's the most difficult to understand. When you have structures, and I think the simulation of the left is even clearer than the right one. When you have structures where all the bodies are connected in many places, so you have over constrained bodies, it's impossible to calculate the loads at all junctions if you don't use flexible bodies, because the flexibility of the bodies is distributing the internal loads, is governing the internal loads, and the solution would not be possible without including the flexibility. If you make rigid multi-body and your bodies are over constrained, the solver will remove automatically the redundant constraints. So calculation of internal loads will be impossible. If you turn the body from rigid to flexible, then there are no longer redundant constraints and you can have all the internal reactions you need. Switching from rigid multi-body to flexible multi-body, of course, introduces a number of new elements in the formulation. For any rigid multi-body is using the well-known theory of rigid body motion in space. So any body is just described by its center of mass and moments of inertia. You don't have any stiffness or damping for the body, and the body has just 6 degrees of freedom. So starting from the number of the body, you can essentially derive the numbers of degrees of freedom. There are very well-known formulas to do that. And of course, if you know where a rigid body is in space, you know everything of any point belonging to that body, because all points are moving with the body reference system. A flexible body is a much more complex entity, because the properties are no longer constant and are distributed. So center of mass and the moments of inertia might change during the simulation because of the deformation, and the stiffness and damping are distributed. The number of degrees of freedom for a flexible body is normally much higher because, yes, you might know where the body's origin is, you might know how the body is oriented in space, but you still need to describe how it is deformed. This was missing in the rigid body formulation, but today for flexible body, we have to say something about the position of the points with respect to the reference marker. So the description of the deformed shape adds a lot of complexity in the mathematics behind the model formulation. How can we represent distributed properties? Well, we still need to deal with inertia, damping, and stiffness. These are the basics of dynamics, and we have to find a way to represent these quantities. Although they are now, when I say now, I mean in flexible bodies, although they are now related to something that changes in shape and position in the space. This is done through matrices, and these matrices are big or small depending on the formulation, and they are containing the information for the solver. In order to build a matrix describing the inertia, the damping, and the stiffness that is distributed in a flexible body, we need to mesh the body. We start from a continuous system, it was rigid. We need to convert it into a discrete system of nodes and elements, like in the finite element approach, no difference. Because once we have this number of nodes, we can play with the quantities related to the nodes, depending on the theory we apply, and we then can describe how these nodes moves each other to return the flexible behavior. So the discretization is a mandatory step to go from rigid to flexible. And in multi-body, we have to take in mind that transforming a rigid body into a flexible one is going to increase a lot the size of the model. Increasing the size of the model has a lot of consequences in the computational time, because multi-body, at least today, cannot benefit of HPC. What does it mean? Due to the structure of the matrices in a multi-body problem, we cannot run the solution on more CPUs, more than, let's say, 2, 3, 4. And these CPUs are just working in parallel, not over a piece of the problem. So parallelization is not allowed in multi-body, at least today. And so increasing the size of matrices can return very long calculation time. The only way we have today to make faster simulations is to go for fast CPUs. And the other thing to do is to use a well-conditioned set of formulas, of equations. This is done inside RecurDyn because RecurDyn solver has been developed and optimized for flexible multi-body simulation. So never forget that using flexible bodies transform a small problem into a big one. The other aspect dealing with flexible bodies and flexible multi-body simulation is the way that the loads are transferred to the bodies. If you are in rigid multi-body, each body is an abstract entity. As said, it's just a marker, reference marker, with certain properties, inertial moments, moving in space, and you can imagine that any point belonging to that body can be used to apply a load, and there is no relation with the geometry that you had to extract the inertial properties. So working with that system is just a matter of size, coordinates, and nothing more. In RecurDyn, you don't see any difference between applying 3 forces, 20 forces, and you don't have to take care of anything in rigid multibody. If you are dealing with flexible multibody, you have deformable structures, and the loads, the way you apply the loads to the body changes the way the body will respond to the load. So it's no longer possible to simplify this transfer of load to the flexible body. If you use a load applied on a single node of a flexible body, you will have local effects that are completely unrealistic. You cannot do that. You can do that in rigid multibody because there is no deformation, but in flexible multibody, it doesn't have any sense. Second, if you want to apply loads to a flexible body, you have to distribute that load over a certain extent of surface, because this is what happens in real life. And so the shape of the geometry, the curvature, the extension, they all matter. And it's important to select these areas before making the body flexible. In RecurDyn, we have 2 options to apply loads to flexible bodies. One is the use of contact, and this is the most intuitive because you just select areas or lines and you involve those areas and those lines in contacts. The second option is the creation of abstract supporting structures we call FDR in RecurDyn. They might be rigid or deformable, depending on the options you set, but these are connecting structures that goes from one body to a number, from one node to a number of nodes located on the flexible structure. Why do we need these FDRs? Because normally when we have a joint or a force applied on a body, it's located on a known coordinate, on a known point. So we start from a single point, but the effect of the force must be transferred to the body, and the body is has its own extension, its own distribution. Let's make an example to make it clear. In this case, we are starting from this rocker that is connected to the valve and to the connecting rod through 3 joints. So we have 3 spherical joints, and 3 spherical joints means 3 precise coordinates for the joints. How can we make these connections if we convert the rocker to flexible? And this is what I mean with FDR. If we need to transfer the force from the joint origin to the body that is now flexible, we need these FDR structures. The FDRs are like spiders. So the load from the master node, this is the master node, the starting of the FDR, is then transferred to a number of nodes on the flexible body. This operation must be repeated for all interface points. Another option is for the contacts. Take this body. This is the follower. Here we have the cam. This body is again interacting with ground and with cam through contacts. The yellow surfaces are contact surfaces. When we create the flexible body, the surfaces, the yellow surfaces, become element patches. So we just keep the same thing we had before, but instead of having surfaces, we have elements on the surfaces. This is the way that RecurDyn treats contacts in flexible bodies. As you have seen, no matter the formulation we will use later, the mandatory step to go from rigid to flexible multibody is to mesh, to discretize the rigid bodies. The meshing can be performed inside RecurDyn or outside RecurDyn. Let's start from outside. If you use an external mesher, you might have your own code, finite element code to do mesh. We can read and we can import that mesh in RecurDyn. But if you do that, when you do that, you have a completely new entity in the model. So when I import the mesh, I have a new body in RecurDyn. This also means that I need to create manually all the supporting features, and which are, as said, FDRs or element patches. And then I need to connect the master nodes to the other bodies with the joints, with the contacts, whatever it's necessary. So using external measures is possible, but you have to do some extra work to reconnect the body to the rest of the model. If you start from a rigid multibody, then you can get a lot of benefit using the internal automesher. Why? Because automesher is a smart tool. It automatically recognizes the joints and the contacts that have been previously defined on the rigid body. So when it applies the mesh, it automatically creates the FDRs and automatically creates the patch of elements for contacts. So any work that you have done before is kept using the internal automesher. Nothing is lost. Additionally, you save time because you skip all the mistakes that might arise by importing entities created outside. This is very common. You create a mesh outside, you set a coordinate for a master node that is not correct. When you import the body, you discover that the master node is not in the right position. So then you have to go outside again, correct the mesh, re-import the mesh again. If you mesh internally, all of these mistakes will never occur. As said in the introduction, in the agenda of today's webinar, RecurDyn has two formulations for flexible multibody simulation. Let's start from the most complicated one. It's the most complicated in terms of numerics behind, but it's the easier to use for the user. The full flex was not invented at FunctionBay. It was first introduced by Shabana and other authors in 2007. But this theory was refined later at FunctionBay, because FunctionBay really wanted to have this unique solver for flexible multibody. The full flex formulation is not far from finite element approach. Essentially, we have the full matrix for the bodies that you mesh, so very similar to finite element. The matrices are built from the measure that you have used, and the size of the problem is really related to the number of nodes that you include and the numbers of degrees of freedom per each node. This changes with the type of elements, so it's 3 for solids, 5 or 6 for shells and beams. So if you have 10,000 nodes, you might have 30,000, 50,000 or 60,000 degrees of freedom per that body. The damping matrix is built starting from stiffness and mass as done in finite element theory. So this is known as Rayleigh criterion. In RecurDyn, we only use the stiffness matrix, so the damping matrix is just a fraction of the stiffness matrix. Of course, if you know the theory behind, you can calculate the coefficient beta to obtain a certain level of damping ratio for a chosen frequency. The full flex formulation is really in competition with finite element because it's essentially a transient finite element simulation. You can use any type of material formulation, hyperelastic, elastoplastic, whatever you want. You can take into account large deformations and rotations. There is no restriction for bodies interfaces. This means that you can have contacts extending as much as you want. This means that you can apply joints and forces involving how many nodes you like. So you can do really whatever you want. In this area, RecurDyn is in competition even with the explicit finite element solvers. What's the difference between RecurDyn, full flex formulation, and finite element simulation? It's essentially in the solver. RecurDyn solver still is and remains a multibody solver. So it has different way to solve the equations. It converges all the time. You don't have the problems that you might have experienced in finite element approach. It's of course slower because we cannot run in parallel on multiple CPUs. But if you're handling relatively small models, then combining the efficiency of our solver with the fact that you don't have any convergence issue, the total calculation time, or at least the total time from when you start to work and the instant you get the results, is comparable or shorter with respect to an explicit solver. So using full flex might be tricky in terms of numerics, but for the user it's not a problem because you just set the mesh, define the properties, and go for the solution. Just wait a bit longer than a rigid multibody, and you will get a real transient finite element simulation and multibody. The other approach, which is included in RecurDyn, of course we couldn't miss it, it's the reduced flex. The reduced flex is known with many different names in the community: component mode synthesis, model reduction, Craig-Bampton method. All of them are different names, but the theory behind was invented by Mr. Craig and Bampton in late 60s. And the theory is a linear theory. So the assumption is that the deformation of a body can always be expressed as a linear superimposition or linear combination of vibration modes, I set X for the number, and constraint modes, I set Y for the numbers. So even if you start from 500,000 nodes in the mesh, the problem size for that body will be X plus Y, regardless the size of the mesh, because we are looking at the deformed shapes of the body. Actually, this approach, this method was invented in late 60s to reduce the size of finite element models when the computers were not that powerful. So the mesh can be big, but the number of unknowns is small. What are the restrictions of this approach? Well, restrictions are a few, but very important. So we always need to know a number of master nodes. Master nodes are the candidates to exchange loads with the rest of the model or with the rest of the world for the body being made flexible. So in order to know these points, these master nodes, we have to consider that this body has to not be involved in contacts where the extension of the contact surface is very large or where the contact is moving over the body. Because in these two conditions, it's difficult to identify a single node through which the load is going through. For joints and concentrated forces, it's much easier because we know very well where the constraint, where the force is applied. So that will be for sure a master node. The second restriction is that the deformations of this body must be small because the approach is linear. So in order to describe the body deformation as a linear combination of other deformations, all of them must remain small. In reduced flex formulation, as well as we had in full flex formulation, we have to connect the body with the rest of the model, with the rest of the world. As said, we look at the master nodes. These are mandatory for reduced flex formulation, and the master nodes are then connected to a number of other nodes selected in the body. The master nodes will be then used to connect, to make joints, to make forces, to make constraints. But the effect of that constraint will be distributed over a number of nodes. You understand that if you have a contact, this is still possible if the contact patch is small, because the master node placed at the centroid of the contact patch is still doing this job. So the connection through FDR is acceptable if the extension of the surface is not that big. This is the reason why we can't keep very large contacts if we expect to use a reduced flex formulation. As said, the number of unknowns, regardless the number of nodes in the mesh, will be x plus y, vibration modes plus constraint modes. The vibration modes are essentially the extracted performing model analysis of the structure with all the interface nodes fixed to ground. This is known as fixed interface model analysis. Mr. Craig and Mr. Bampton have found that this is the best approach. Other theories use free interface nodes or elastically constrained interface nodes. But for multibody, this fixed interface model analysis is the best one. How many frequencies should we keep in this model analysis? This is the big question. But in practice, it's good to keep a number of frequencies big enough to have the highest frequency that is exceeding the highest frequency that we expect in the simulation. Let's say with different words. If we are running an engine or something and we have the rotor running at 1000 hertz and we have some flexible parts dealing with this rotor, we should keep a number of modes so that the highest mode has 1000 hertz or more. In my personal experience, I normally keep double or 3 times the number of modes that is suggested by this rule. So if the rotor is running at 1000 Hz, I keep modes up to 3000 Hz. Because in this calculation, it's better to keep more modes. You can deactivate the modes that are not necessary later. For the constraint modes in this analysis, we don't have to say much, because these constraint modes are defined by the number of interface nodes and the number of degrees of freedom per node. Since we are in space, we have always free translations and free rotations, so each interface node has 6 degrees of freedom. So the Y is essentially 6 by the number of master nodes. A step forward in this reduced flex approach is the orthonormalization. We need to put all the shapes given by the model analysis, X, and the shapes given by the constraint analysis, Y. We need to put all of them in the same matrix, and then we have to make sure that all of them are linearly independent. This is the purpose of the orthonormalization procedure. The orthonormalization returns the same number of modes expressed in a different base. Sorry, it's mathematics behind. And the purpose is to have all of them linearly independent. This is necessary for the solver later to find the coefficients that combine the modes. Take in mind that the change of basis makes the modes no longer physical. So you start from constraint modes and vibration modes that are all physical, and you end with a set of modes that are non-physical modes. This is important. So the solution is performed in a set of coordinates that have no physical meaning, but the solver can find them. Once the solver has found the coefficients to combine the modes and return this linear combination describing the deformation, then you can go back to the physical coordinates, and this is done in post-processing. But the solution is done in a system of coordinates that are completely abstract. How can we use the reduced flex bodies in RecurDyn? Again, we have two options. We can either read from ANSYS, Nastran, or IDEA's finite element codes. We can read the results, and everything has to be done outside RecurDyn. Of course, if you import results that are created outside RecurDyn, you have again manually to create joints and contacts and forces to reconnect this body to the rest of the model. Anytime you import something in RecurDyn, it's a new entity. It has nothing to do with existing parts or bodies. If you do the reduced flex generation inside RecurDyn, then you have everything saved. And this is possible because RecurDyn features an internal finite element solver that is optimized to make this Craig-Bampton analysis. By applying this solver to existing full flex bodies, so to existing meshes, you obtain the reduced flex bodies immediately, automatically, without risk of errors. Because you are not importing anything from outside, you are just reusing work that has been done previously. For the damping controls, as said, in full flex you apply the Rayleigh method, and there is nothing to say about this. It's a well-known approach. You calculate the beta coefficient depending on the damping ratio you want to have at a certain frequency, and this beta coefficient is inserted in RecurDyn among the material properties. This method is not precise in the sense that it makes sure that the damping ratio is correct only at a given frequency, but this is everything that can be done in finite element. With the reduced flex approach, the damping is applied in a totally different way. As said, the reduced flex body is a set of modes with no physical meaning. So the only thing you can do is give a damping ratio to each mode, and where of course 1 means critical damping and numbers below 1 are fractions of the critical damping. This damping is not physical. So if you wanted to have a certain damping for a reduced flex body, the only thing you can do is to tune the damping ratios of the non-physical modes until you get the physical damping that you want to see in your system. So there is no alternative. You have to iteratively run the simulation with different values of these coefficients until you see the damping that you want to get. One feature of RecurDyn that is very useful in getting flexible bodies is the general manager, the G manager of RecurDyn. This is a kind of assistant, virtual assistant, that supports all convention of body formulations, from rigid to full flex, from full flex to reduced flex, from reduced flex to rigid, and vice versa. The purpose of general manager is to avoid mistakes. So if you run inside RecurDyn the conversion with the G manager, you never lose data. You never lose work that you have already done. This is very convenient because sometimes you don't know whether your body has to remain rigid or be modeled through a full flex or reduced flex. So you can try, and if the formulation that you pick is not working, you can go back to another formulation or back to rigid. And all the times you perform this conversion, you don't lose anything in the model. The contacts remain active, the joints remain active, the forces you applied remain active. This is very important and it's very helpful. The general manager works better if the measure is the internal measure and if the reduced flex generator is the internal one. If you have imported external data, it's still possible to use the G manager, but capabilities are limited. Let me now show an application where the use of flexible bodies is important, is mandatory. This valve train is a valve train of an internal combustion engine, a small one. And as you can see from this slide, we have some bodies. Some of them are grounded, some of them are kept together by joints, and some others are kept together by contacts. In this model, for sure, we need to use flexible bodies because the dynamics is happening at very high frequency. So all the frequencies are comparable to the structural frequencies of the bodies. And so we need to make all of them flexible. The point is how? Because as said, we have two options in RecurDyn. We can use either full flex approach or reduced flex. We know that using full flex we have everything, but the computational time will be higher because of a larger number of degrees of freedom. So we have to examine body by body and make a choice, pick a decision. For the push rod, we might observe that this is a thin structure. It's working essentially pushed from top and bottom. The contact areas are small compared to the size of the body, and essentially we can imagine there is a master node through which the load is transferred to the body at each end of the rod. So apparently the reduced flex formulation is going to do the job pretty well, but we don't have to forget that in case of nonlinear behavior, the reduced flex formulation is not good. But in this case, we can imagine small deformations, and so reduced flex is probably the first choice. I've been pointing out in this slide also the number of degrees of freedom if you have a reduced flex approach by keeping 40 fixed interface modes and 6 constraint modes per each master node. Then yes, the number of unknowns, which are the coefficients used in the linear superimposition, are just 25. So using reduced flex approach, this rod is described by 25 unknowns. If we keep the full flex formulation with this number of elements and nodes, we have roughly 15,000 degrees of freedom. So 25 versus 15,000. You understand how the computational effort is going to be affected. The rocker body. This has no joints. Contacts are again small in extension compared to the size of the body. And the centroids of the contact areas are not moving with respect to the body. So again, we might think to use a reduced flex formulation. The picture is showing you how the FDRs, so the connectors, are created inside the mode. And again, considering 40 fixed interface modes, for this solution we can run with 20 modes, because the range of frequency is between 12,000 and 70,000, which is more than enough. The third body is the follower. Even this body has no joints. The contacts are medium to large extension compared to the size of the body. So here it's becoming difficult to decide where to place the master nodes. We need to know the master nodes to apply the reduced flex formulation. If it is not possible to know the master nodes, and these master nodes are not fixed with respect to the body, then we are forced to use the full flex formulation. In this case, we go for that, because especially for the contact between the follower and the cam, there is no possibility to set this master node. So in this case, we have 28,000 degrees of freedom, and we have to live with that. Here is the result we obtained. So the model is working pretty fine, and I'm showing the von Mises stress for the structures, and you see there is a clear effect of inertia. You see also the follower is not keeping the contact with the cam. This is due to the fact that intentionally I've placed a spring that is too soft. This was intentional for the simulation. So we will have this floating of the valve, and also the floating of the follower. But this is not the most important part for my simulation. As said, we went for the reduced flex formulation for the rod, which is linear. But in this case, the connecting rod is working in a non-linear way, because the buckling load is causing the structure to deflect laterally. And this will happen for sure even in the real engine, because this is a very thin structure. So if we keep a linear approach, we can never capture this out of plane deformation. In this case, the reduced flex approach is not suitable. We have to use full flex because of the buckling. Even if we have two clear master nodes, even if the material is linear, even if the contacts are limited in extension, we have to keep the full flex. Without full flex, you would not get correct results. And you understand here what I'm saying, because if we measure the valve lift with different combination of a reduced flex and full flex and the rigid formulation for the bodies involved in this model, you see that the measurement of the valve lift changes a lot. So if my model is made to capture the real behavior of this valve, I cannot make wrong choices. In particular, in this case, if I don't use the full flex approach for the rod, I will get results that are 0.5 millimeters wrong. I think this is also important to measure the performance of RecurDyn, the efficiency of our solver. In this table, I've collected all the tests I've made with this little model. So the number of degrees of freedom is taken from the log file from the solver, and the CPU time is the time that I measured in the computers that I've used. Unfortunately, I could not run all tests on the same machine, so the latest two tests are made on a faster CPU. But the important effect to capture from this table is that there is, of course, a relation between the number of degrees of freedom and the CPU time. This relation is not linear. You see that going from the first to the second, although the number of degrees of freedom is growing a little bit, the CPU time is going down by 1 minute more or less. And then you see that increasing again the numbers of degrees of freedom, third line, the time is almost double, and so on. Why isn't the response linear? It's very simple, because it's dynamics. Whenever you change the formulation of one of your bodies, the response of the system is going to change as well. And it might change in a direction that is good for the solver or in a direction that is bad for the solver. So you might have more iterations of the solver at a given time step. So the relation is not linear, but we have to live with this because this is dynamics. The other comment that I want to spend on this table is about the calculation time. You see, let's take the latest row. You see that even using full flex formulation for all bodies, which brings almost 80,000 degrees of freedom, we still have a reasonable calculation time. Consider that the setup of this model is quite fast. If you have to make this model in another environment like an explicit finite element, or if you want to make it in an implicit finite element code, the solution time will be for sure longer. So the messages to take home for you today, I think that I've shown you that RecurDyn has many features to build multi-flexible body models. Especially the internal auto measure, the reduced flex generator, the general manager are all features that are fully oriented to assist the user in the creation of the flexible bodies. The solver is quite efficient as I've shown you. Even with large number of degrees of freedom, the calculation time is still good. And you don't have to forget that multi-body solver is not running using parallelization. It's completely running in a straightforward way. So the speed is really related to the quality of the solver. Of course, using faster CPUs is better. You can have a model that features rigid, reduced flex, and full flex variously combined in the same model. This is not a problem for RecurDyn. If you want to use the reduced flex method, this is the most convenient in terms of computational time, but you have to take care of the limitation of this approach. This is general. This is not for RecurDyn. And we have understood that this is not good for large contacts, is not good for nonlinear materials, but it's not good even if you have second order effects like buckling. And I've shown you an example where this is happening. The full flex method is pretty good. RecurDyn is the only one that has this approach in among the products that are available in the market. And full-flex has no limitations, but keep in mind that it increases a lot the number of degrees of freedom. In case you want to have more information about RecurDyn, you can surf the web and search for information at recurdyn.com or functionbay.com. It's also available the support forum for the RecurDyn users, but you can visit it as an external user. You can access the online help. RecurDyn is probably the only technology that is sharing its online help. And in case you want to know more about, you can even pick the phone and make me a call or send me an email. I'm available. You can also find me on LinkedIn, and you can chat with me on LinkedIn. I hope this webinar has satisfied your expectations. I did my best. Sorry for little mistakes in English, but this is normal for foreigner. So I hope you enjoyed it, and I wish to thank you for watching and listening this webinar about RecurDyn capabilities for flexible multi-body simulation.